All right, so we'll be kicking off session 2, Ocean Processes and Predictability in the Pacific. So I'm your one of your moderators, Sarah Larson, and your other is Antonietta Capitandi, and she'll be moderating the discussion session. So we've got 4 talks, each 10 minutes each. So if you're speaking in this session, I have a microphone over there at 8 minutes. I'm going to say 2 minutes left, so don't be alarmed when that happens. So first up, we have Xian Wu at NCAR, and the title of her talk is 2-Year Dynamical Predictions of ENSO Event Duration during 1954 to 2015.
Hello, everyone. My name is Xian Wu, and I'm currently a postdoc working at NCAR. I'll be talking about the 2-year predictions of ENSO event duration. The work was part of my PhD thesis work done at UT Austin with Dr. Yoko Okumura, my advisor, and collaborators Clara Deser and Pedro Dinazio. The motivation for us to focus on the duration of ENSO events is the prolonged climate impacts that could be induced by multi-year ENSO events. For example, multi-year La Nina events can produce 2-year consecutive drought conditions over the southern US. And you can see in the right panel, in the second peak of the La Nina events, the drought condition over the southern tier of the US persists and extends northeastward. It is therefore important to understand the dynamics of ENSO event duration and predict the occurrence of the long-lasting events with sufficient lead times. The ENSO, here the NINU 3.4 index shows that ENSO events show a wide range of durations, and about 30% of El Nino events and half of the La Nina events lasted 2 years or longer over the historical record. Our previous diagnostic study has looked into the factors and mechanisms that control the duration of ENSO events. We also tested the potential predictability of duration of ENSO events using the perfect model experiments. In this talk, I'll be focusing on the real-world prediction scale. The current operational forecasts of ENSO are limited to up to 1 year, precluding the predictions of multi-year ENSO events. So we conducted 2-year lead forecasts with CESM2 during 1954 to 2015. 10 to 40 member ensemble forecasts are initialized with the observed oceanic and sea ice states on March, June, and November 1st of each year during 1954 to 2015. And ensemble spread is created by adding small perturbations to the atmospheric initial conditions, and we expect that the 2-year predictability of ENSO events mostly arises from the oceanic initial states. These forecasts are also conducted under the CIMIC 5 external forcing. We used the traditional way of lead time dependent drift correction to get the forecast anomalies, and we also detrended both observational and forecast anomalies to get rid of the scale that arises from predicting the anthropogenic warming trend. For each ENSO events, we compare the forecasts initialized at the 6 different lead times relative to the December +1, about 1 year after the first ENSO peak in December 0. So we have the lead times range from 25 to 6 months. Here I'm showing you the forecast example of the strong El Nino in 1972. The development and termination is first captured in the forecasts initialized in March 0 in red curves, but the development of subsequent La Nina is first captured in the forecasts initialized in November. And in the left panel, I overlay the ensemble mean forecasts for this case. And we will expand such comparisons to the composites of all 1 year and 2 year ENSO events. For the 1 year El Nino, we can see its development and termination is first captured in the June initialized forecasts in yellow curve. And we can identify the maximum lead time of predicting the duration for all other 3 types of ENSO events as listed below. Most prominently, the development and persistence of 2-year La Nina can be predicted with the longest lead time of 25 months when the model is initialized from the preceding El Nino. And overall, we find that the November initialized forecasts can predict the duration of both El Nino and La Nina with 13-month lead. And I'm not showing the correlation scale of Nino 3.4 index here. We find that the useful scale can persist into the spring after the second peak. So that will provide a useful scale of about 1.5 years. Next, we'd like to understand what are the dynamical processes behind the prediction scale. Here, I'm focusing on the equatorial Pacific processes. I'm showing you the sea surface temperature anomalies in color shading, thermocline depth in black contours, and surface wind anomalies in vectors for the equatorial Pacific for both 1 year and 2 year El Nino in observation and forecasts initialized near the peak of the El Nino. In observation, 1 year El Nino tends to develop about 2 months earlier than the 2 year El Nino and have a stronger peak amplitude around December 0. And this earlier onset of El Nino will lead to an earlier arrival of the strong delayed oceanic feedback as indicated by the negative thermocline depth anomalies in the Western Pacific. In contrast, the thermocline shoaling occurs a few months later in the 2 year El Nino. So the November initialized forecasts are initialized with opposite signs of thermocline depth anomalies, and they show distinct evolutions in the subsequent seasons. In 1 year El Nino, the negative thermocline depth anomalies propagate eastward, leading to the termination of El Nino event, while in 2 year El Nino, this thermocline shoaling occurs later and cannot arrive at the eastern equatorial Pacific in spring, and El Nino starts to re-intensify in the summer season when there is a seasonal intensification of the Bjerknes feedback. The timing effect of thermocline feedback also appears to be important to the predictions of La Nina events. You can see here the November initialized forecasts are also initialized with opposite signs of thermocline depth anomalies in the Western equatorial Pacific. But we also find that the initial thermocline shoaling across the equatorial Pacific, its magnitude is important to the predictions as well. The 2 year La Nina are initialized with stronger negative thermocline anomalies, and it will help La Nina to last longer. And this initial thermocline shoaling is associated with this amplitude of previous El Nino. So when the forecasts are initialized from the peak of preceding El Nino, they can also well capture the 2 year La Nina events.
2 minutes.
Thank you. To summarize, we found that the CESM1 shows high skill in predicting the duration of both El Nino and La Nina with lead times ranging from 6 to 25 months. In addition to the initial thermocline depth anomalies I've discussed here, we also find the predictability could come from the initial states within and outside of the tropical Pacific. In our published paper, we also looked into the forecast ensemble spread, and we find it's shows dependency on the lead times and ensemble mean state, and it mainly originates from the atmospheric variability over the North Pacific. The 2-year lead potential predictability of ENSO event duration indicates the potential of extending current operational ENSO forecasts to 2 years and may also provide a source of predictability for the associated climate impacts. Thank you for your time.
Great, thanks, Xian. Next, we have Youngji Joh at NOAA GFDL. And the title of the talk is Seasonal-to-decadal Variability and Predictability of the Kuroshio Extension in the GFDL Coupled Ensemble Reanalysis and Forecast System.
Thank you very much for the opportunity to speak. My name is Youngji Joh from Princeton University and NOAA GFDL. I first would like to recognize my valuable collaborator and resources from NOAA GFDL. The Kuroshio Extension is the major part of the Pacific Western Undercurrent system, and this is the inertial eastward jet related to the Kuroshio current. And the Kuroshio currents are bringing the warm water from the tropical Pacific to the mid-latitude. So the Kuroshio Extension is a key region to release substantial heat from the ocean to the atmosphere. And this KE region has been exhibiting the strongest sea surface height variability, as shown in this standard deviation map. And it has the strongest variability due to the strong oceanic current and the mesoscale adductivity. Sorry, can I take this? So yeah, so the Kuroshio Extension SSH has been recognized as an effective proxy for decadal modulation of the Pacific Western Undercurrent system because it can explain the decadal modulation of the eddy kinetic energy level or ocean front as seen in this the time series bottom here. You can see there is a strong covariability between KESSH and the ocean front position, especially the meridional position of the maximum gradient of the SSH. So understanding and predicting this Kuroshio Extension SSH variability might be helpful to understand and project the ocean circulation and also the physical dynamics of the Western Undercurrent system. So based on this motivation, we explored the representation and prediction skill of the Kuroshio Extension sea surface height variability using reanalysis in the forecasting system. In this work, we mainly use SPEAR model, which is Simile System for Prediction and Earth System Research. This is a coupled atmosphere, ocean, land, and CS model, which was recently developed at NOAA GFDL. While more details can be found in the method section and the related paper, but I just would like to briefly mention that some important feature about coupled initialization reanalysis that were used our decadal and seasonal retrospective forecast system. That is, while our SATM SST has restoring atmospheric temperature winds and SST, where there's no subsurface ocean observation, but ODA, this name is following ocean data assimilation. So it used SST and subsurface ocean observation, but there is no atmospheric observation. So you can see these coupled initializations are very contrastive and very different each other. And by comparing these two reanalyses, we first found there is a significant role of subsurface ocean observation. That was subsurface ocean observation was very important to resolve this for detecting this accurate position of the KE ocean front and also this eddy-related oceanic signature, like this wavy signature of the KE jet, because these features were only resolved in the ocean data assimilation, but were missing in RSA TMSST. And but when we looked at the temporal evolution, we found both reanalysis systems were able to detect this reasonable KESSH, which is comparable to the observation of satellite, including this strong decadal spectral peak as shown in this KE power spectra. And in terms of this strong decadal variability, many publications have noticed the wind-induced decadal modulation of the KESSH. So the left panel shows the Hofmüller diagram of the meridionally averaged of the mid-latitude SSH anomalies. And you can see, like this arrow, there are some westward propagating anomalous SSH signal from the mid-latitude to the KE region, providing some deterministic signal and predictability of the KE SSH. And this forcing and the major source of the predictability were very well resolved in our dynamical decadal retrospective forecast, as seen in this middle panel, which is 1-year lead forecast under January initialization. And we found there are some significant multi-year KE prediction skill in our decadal forecast, as shown in this correlation skill of the annual KE SSH. So these black and green lines are indicating the correlation skill between the forecast with the reanalysis and observation of satellite respectively. And you can see the bold lines are indicating the significant prediction skill above the significance level. And you can see there is significant skill up to 5 years regarding the ensemble mean, but especially reliable skill up to 3 years, because this ensemble spread says all the individual model has now higher correlation skill above the significance level. And when we compare the skill from the linear Ross wave model prediction, which just describe these baroclinic oceanic Ross waves based on the linear vorticity equation, we found our dynamical model forecast has some higher correlation than that of this linear Ross wave model prediction. And we attribute this skillful forecast of the KE maybe attributed to the January initialization, because under a stronger amplitude of the atmospheric forcing, it can give a more effective inertial memory to the upper ocean. And from the seasonal retrospective forecast, we found that KE prediction skill is highly dependent on the different initial condition and the target prediction month. These red lines are indicating the short-lived KE forecast skill, and you can see these are relatively flat and constant across the different initialization month or forecasting target month. But when we looked at the long-lived KE forecast skill, it shows the higher correlation skill, highest correlation skill when we use winter initialization, and especially when we target the autumn KE SSH. And as you may feel, this behavior was very similar to the characteristics of the re-emergence mechanism, because once there is some soft surface anomalies are formed in the prior winter, it can remain and having some memory and can communicate with the surface ocean in the following fall. So we think winter initialization may help these soft surface anomalies can have longer memory and can stay longer, and driving some difference in this seasonal KE prediction skill. Before wrapping up the presentation, I just want to highlight the necessity and some benefit of using the dynamical model forecast for the KE prediction. Because of course, the previous linear Ross wave model is very powerful because it also gives some deterministic signal, and it was very successfully predicting these baroclinic Ross waves related the KE modulation. However, in 2017, there was very unexpected phase transition of the KE from the negative to positive phase. And this was very tricky and unexpected because it was not driven by traditional oceanic Rossby waves, but rather induced by the large oceanic meander episode, which can be some irregular or chaotic sometimes. But we found in our dynamical model forecast, following the SSH propagation from the satellite altimeter, these black lines are indicating the initiation and development of the warm meander south of Japan. And you can see the 2017 January forecast also predict this initiation, development, and movement of this meander episode that transitioned the KE from negative to positive. And previous recent publication concludes that this meander episode is not entirely intrinsic episode, but is linked to the regional or large-scale variability. And so we think that was how our dynamical model forecasts were able to detect this large meander episode. So what we've learned, thank you, Sarah. What we've learned from this episode, the KE variability sometimes triggered by this irregular large meander episode. And because of the existence of the strong air-sea coupled and coherent atmosphere and ocean fluctuations, so the dynamical model forecast may be useful, especially for detecting comprehensive KE dynamics, leading to a potential of the real-time KE prediction. So as a summary, we found the GFDL SPEAR forecast models have some significant multi-year prediction scale, up to 5 years and up to 1 year, each decadal and seasonal forecast, respectively. And this was prominent, especially under winter initialization, because winter initialization can provide longer inertial memory to the upper ocean by supporting the reemergence mechanism and enhancing the oceanic Rossby waves with a larger amplitude of the atmospheric forcing. And as the challenges, because we found subsurface ocean observation is critical to detect the accurate ocean front position and some oceanic-related KE spatial structure. So we think subsurface ocean initialization is important for the KE spatial structure. And also there is high dependency of the short lead forecast skill of the KE, because this is more related to the short time, small scale eddy activity. So increasing ocean resolution would be helpful for the short lead for KE forecast skill. This work is recently published in Journal of Climate, and hopefully more details can be found in upcoming publication. Thank you.
All right, next we have Robert Jnglin Wills at University of Washington, and he'll be talking about insights into multi-year and multi-decadal predictability from ocean initial conditions in the CESM2 Large Ensemble.
Thank you, Sarah, and thanks for the opportunity to speak. I'll note that in addition to my primary affiliation at the University of Washington, I just moved to Boulder, where I'll be a long-term visitor at NCAR, and so I know a lot of the audience is Boulder-based, and I'm looking forward to more opportunities for collaboration with all of you. So this project is mostly about longer timescales than we're talking about here. So looking at the multi-decadal dependence on initial conditions of the CESM2 Large Ensemble. But I wanted to present it here both to show that some of the same processes are relevant at multi-decadal and multi-annual timescales, and to show that I think some of the methods that we're using to diagnose the multi-decadal predictability are also useful for diagnosing multi-year predictability. So what this project is doing is it's looking at the role of initialization in the CESM2 Large Ensemble. And so for CESM2, there's 100 members. 20 of them were chosen from different ocean initial states in this period between 1,000 years and 1,200 years in the control run. I'm not going to be talking about those today. I'm going to be talking about these other 80 members, which use 4 different ocean initial states. And each of those 4 ocean initial states, which are chosen to represent different values of AMOC variability, so going from a high AMOC state to an intermediate to a low and back to an intermediate. Each of these are run with 20 ensemble members, where those 20 ensemble members differ by their small perturbations in their atmospheric initial state. But they all have the same ocean initial state. So the research questions we're interested in here is how long out into the simulation does this choice of ocean initial conditions matter? What processes are leading to this dependence on initial ocean state decades or centuries into the simulation? But then switching more to the theme of this workshop, on multi-year timescales, what processes lead to multi-year predictability, just taking as an example these 4 ocean initial states in CESM2, and using the same methods to diagnose the mechanisms of multi-year predictability as multi-decadal predictability. And also just wanted to demonstrate the utility of the signal-to-noise maximizing pattern filtering method that I'm using to diagnose and help identify predictable signals. So I'm going to be talking about a variance decomposition where I split the variance within the CESM2 Large Ensemble within these 80 ensemble members into that due to atmospheric initial conditions, so variance within the 20-member micro-ensembles, and variance due to ocean initial conditions, so variance between these 4 micro-ensemble means. And I'm also going to be talking about this fraction of variance that's predictable from ocean initial conditions, which I'll call chi. So what I'm going to be using is a signal to noise maximizing pattern analysis, which is in this case based on EOFs. It finds a linear combination of EOFs, so some spatial pattern that maximizes a signal to noise ratio. This has been used for a wide variety of applications. And in particular, in a recent paper, I've used an application of it that I call pattern filtering that combines these signal noise maximizing patterns back together into a spatial temporal data set. And I've shown that this can help you identify forced responses with up to 10 times fewer ensemble members than an ensemble mean. So this was for the case of forced predictability in this paper, but here I'm talking about this initial value predictability based on the differences between these different ocean initial states. So I'm defining signal as a difference between the microensemble means and the noise as the differences within these microensembles due to atmospheric initial conditions and the resulting noise from that. So here's the first look at the multi-decadal timescales. This is looking at 5-year averages going from the start of the simulation out until 2100. And the signal noise maximizing pattern 1 is basically the AMO. It's related to AMOC. There's been a lot of work on how this is AMOC responds to stochastic NAO variability, and I think that's what's going on here. This predictability measure, chi, shows predictability out for 50 years into the simulation when you talk about these 5-year averages. So definitely some predictability there out to very long timescales. Interestingly, you also get predictability out even further into the simulation, not quite as high, but coming from Southern Ocean upwelling and connections into the tropical Pacific and into the North Pacific and North Atlantic as well. So you get skillful prediction based on this bootstrapping significance threshold measure shown in a dashed line there, out at 1900, so 50 years into the simulation, and even out at year 2000, 150 years into the simulation. And if you look at the associated zonal mean ocean temperature anomalies, just regressing them onto this these time series, you see that this one is related to uptake of ocean heat content in the North Atlantic, and that the second one is related to upwelling of ocean temperature anomalies from in the Southern Ocean, as well as some other things. There's still a lot of mechanistic parts to figure out here. Some preliminary results. Now, transitioning to multi-year timescales, I'm basically doing the same analysis, focusing on the first 10 years of the simulations and looking at 3-month average surface temperature anomalies. Switched from SST to surface temperature simply so that I can show some predictions of surface temperature, which are a little bit more societally relevant. Of course, the SSTs help you get there, so it's useful to have the SSTs in the field as well. The first pattern is much the same as in the multi-decadal case, other than that you have these additional surface temperature anomalies over sea ice and land and so forth. So this is associated with AMO and AMOC and gets you predictability. So you can see these different ensemble members, these 4 different ocean initial conditions. I forgot to explain this middle plot here. These are all the ensemble members and the ensemble means of those. In the solid line, the darker line is the ensemble means. So you can see that these remain separated with skill out for the first 10 years. I'm showing just years 2 and beyond here, so focusing on multi-year. Then you get a number of other patterns. I don't think mechanistically they're giving you a whole lot of insight, but it gives you a way to identify all the different regions that are important and then combine them back together in different ways. So you could, for example, put these into a linear inverse model that just focuses on the significant signal noise maximizing patterns. So here's something also with Southern Ocean upwelling and teleconnections to the North Pacific. Something different flavor of different superpositions of that as well. Then something like the PDO, which is getting you significant predictions out into year 2, but not so much beyond, maybe a little bit at 5 to 7 years. Remember, this is in 3-month means. So not very high predictability, but statistically significant compared to random noise, at least. So then how could this be useful? So in order to diagnose if in, for example, a more societally relevant measure like the US Southwest summer temperature anomaly, you do need to look at the raw data. So this just within the CESM2 Large Ensemble, but the raw data there shows that there is potentially some predictability there. This chi value is significant compared to random noise. What the pattern filtering can do is it's combine back together these signal noise maximizing patterns and help you identify that predictable signal with fewer ensemble members. So you still need to see in the raw data whether this is actually predictable, but if you know it's predictable, then the pattern filtering can help you get there more efficiently. So basically the proposed strategy I'm suggesting is that you could use pattern filtering to extract the predictable signal, then use some estimate of interannual variance to determine whether that's actually a detectable prediction or not.
2 minutes.
Okay, went a bit fast. So in summary, the choice of ocean initial conditions impacts the surface conditions for at least 50 and up to 150 years into the simulation. This is related to processes in the deep ocean, particularly Southern Ocean upwelling. In the first 50 years, AMO and AMOC gives you a lot of predictability. Then on multi-year timescales, the AMO and AMOC is still the most predictable thing because it's predictable on even longer timescales. Then various flavors of PDO and Southern Ocean. So it's not really one mode here. It's a whole variety of different processes in the Southern Ocean upwelling zones and in the tropical and extratropical Pacific lead to multi-year predictability. And signal noise maximizing filtering can help you isolate the predictable signal, where then you just need to understand whether it's detectable or not by looking at some measure of the interannual variance in the quantity you're trying to predict. So thanks, looking forward to the discussion.
So our last talk in this session is a virtual participant. Is that correct? Yeah. Okay. So we have Hui Ding at University of Colorado CIRES and NOAA PSL. And he'll be talking about mining large climate model datasets to make actionable multi-year initialized sea surface temperature forecasts.
Yeah, I'm going to talk about mining large climate model datasets to make multi-year initialized global SST forecast. And here I want to introduce my co-workers. And I'm Hui Ding, and I have done this work with Matt Newman, Mike Alexander, Andrew Winterberger, Ian Wang, and Sam Lino. So this slide is about our motivation, and this figure shows 6-month need SST forecast scale. And in the upper panel, it is calculated from 4N MME models ensemble mean. And in the bottom panel, we apply a simple model analog method to the same 4N MME models. By comparing these two panels, we can see the analog method reproduces SST forecast scale in the tropical Indo-Pacific, and this motivates us to make multi-year SST forecast using the model analog method. And this slide is about model analog method detail. So our data library is a long control simulation, and this is different from previous studies about analog forecast. And for given initial observed state. So here observed state is defined by observed sea surface height and the SST anomalies globally. So for given observed state, we search our data library and found the nearest states, which are analogs by definition. Since we already know time evolution after analogs in the control simulation, we can immediately use them to predict time evolution after the initial observed state. So our model analog forecast is a following time evolution of analogs, and we often take on some of 10 or 20 nearest states. And here we use a root mean square distance to measure similarity between states. And also analogs are constrained to be from the same calendar month. And in this work, we use control simulations from 4 models. So these 4 control simulations are our data library in this work. And here in this figure, we show global SST forecast scale in year 2 on the left and year 3 on the right. And for this figure, we apply the model analog method to each month over the years 1961 to 2015. And for year 2 forecast, we can see SST anomalies in some regions are predictable, and we can see a correlation value of 0.3 and 0.4 in some regions. For example, the Equatorial Pacific, North and South Pacific, and we also see it in the Northwestern Tropical Atlantic and Southwest Indian Ocean. And for year 3 forecast, and we still see a correlation value of 0.3 in the Southwest Indian Ocean. And here we show the time evolution of forecast scale for SST anomalies in the ENSO region. So what is shown is pattern correlation in the ENSO region, bounded in this area. And in this figure, the x-axis is verification time, and 6 month need forecast scale is this black line. And for other 3 need months, pattern correlation value of above 0.4 are shown only, and red and blue shadings indicate El Nino and La Nina events. From this figure, we can see pattern correlation tend to be higher during El Nino and La Nina events when the ENSO activity, when the ENSO activity is strong. And for some ENSO events, not all of them, for some ENSO events, the pattern correlation is still about 0.8. For example, this event and also this event. And even when we initialize the forecast 24 months ahead, so this suggests multi-year forecast opportunity for some ENSO events. And here we use the La Nina events in DGF 99-2000, for example. So here we show the forecast of this La Nina event, and forecasts are initialized from different times with need times from 36 months to 6 months. And in each panel, the black line is observed Nino 3.4 SST anomalies, and the blue line is multi-model ensemble mean. And we also show ensemble members, and they are thin solid lines. And if I look at the black and the blue lines, we can see this La Nina event is predictable at least 2 years ahead. For example, for this left mid panel, in this panel we initialize forecast 30 months ahead, and we can see the ensemble mean forecast well captures the evolution of Nino 3.4 SST anomalies and then predict the La Nina event in DGF 99 and 2000. And here, for long need forecast, one important question is, can we identify which long need forecasts are scalable when we make the forecast? And according to our results, the answer is signal-noise ratio. So in the upper panel, we show Nino 3.4 SST anomalies from observations and multi-model ensemble mean forecast. And the x-axis is the time axis. It could be initial time and valid time. And for the y-axis, the bottom row is observations, and 0 means initial reconstruction, and above are ensemble mean forecasts with need times 1 to 36 months. So in this figure, we show all the verification and all forecast. And the forecasts are initialized from each month of the years 1961 to 2015. And all forecasts are verified against observations at the same point as the x-axis. For example, we can use the 97-98 El Nino event as example. And here is at the bottom row and its observations and zero, and we can see initial reconstruction will capture the 97, 98 linear event, and when we reach up their ensemble mean forecast with increasing lead times, and we can see this linear event it can be expected about 12 months ahead. And from this figure, we can also see most ENSO events are well captured by seasonal forecasts at about 6 months lead time. And for some ENSO events are also well captured by multi-year forecasts. And in the bottom panel, this bottom panel is the same as the previous one, but it's for signal noise ratio. And we show for signal noise ratio, we show value of above 0.7 only. And by comparing the two panels, we can see when in the upper panel, when the forecast successfully captures the observed ENSO events, the corresponding signal noise ratio in the bottom panel is above 0.7. So this tells us our forecast scale is a signal noise ratio problem, and this can also help us to identify which long lead forecasts are skillful when we make the forecast.
2 minutes.
Okay, yeah. And for the signal noise ratio, another thing I should mention is the variations in ensemble spread from year to year are only 10 or 20%. So ensemble spread has a very small interannual variations, and the variations in signal noise ratio. So variations in signal noise ratio arise mainly from the ensemble mean. Yeah, here's our conclusion. So model analog method provides a cheap and easy way of making multi-year ocean forecasts, and we can initialize forecasts from every month. And some ENSO events are predictable 2 or more years ahead. And this may be identified beforehand by ensemble mean signal noise ratio. Yeah, thank you very much for your time. Yeah, my talk is over. Yeah, thank you.
Yeah, thanks to all our speakers. And I'm going to hand it over to Antonetta for the discussion section.
Actually, almost out of time, but we can take 10 minutes for this. Yes. Okay, so are there questions online or in the... Okay, Jerry?
I have a question for Youngji, who's actually sitting right in front of me. So I just had a question about your initialization method. And you probably said this and I missed it, but it looked like you were initializing SST from atmospheric forcing and then subsurface ocean from ocean data assimilation. What kind of problems did that cause in terms of the discontinuity between the two? Did you have to do smoothing or were there any problems?
I think I'm not the right person to answer that question because I used completed ocean data assimilation, reanalysis. So I have no idea what's going on. But could you explicitly ask your question, mention your question again? What the discontinuity you mean?
Yeah, so I mean, we've been people. This is an outstanding issue for the initialized prediction on these different timescales: is how best to initialize. And so this is kind of one of these research questions that people are wondering about. There's no good best practice for this, right? For these longer timescales, and so that's why I was kind of intrigued by this mixture between you're kind of doing this apparently in a hybrid kind of initialization where you're doing some kind of ocean data assimilation to the subsurface, which makes a big difference for your results, right? Because you need that ocean subsurface. There's the Ben Kirtman brute force method where you just stick in the ocean reanalysis data directly, or you can try to assimilate ocean data from observations, which is of course more complicated, more expensive, or you can do do this kind of atmospheric forced initialization, the so-called FOSSI or forced ocean sea ice, which is what UCAR's been doing for a while and other people have done, where you're just forcing the surface of the ocean from observed atmospheric forcing, run it through the 20th century a few times, and then you kind of imprint that forcing in the upper ocean. But that's not assimilating the subsurface ocean, so you're going to have distances from observations for that. So I think you didn't do this, obviously, but I think this is kind of an interesting question for this group, is how best do you assimilate, what gives you the best results, and how relevant is that to this problem we're looking at these kind of 2 to 10-year timescale predictions?
Yeah, and I think this is particularly important in an area like the Kuroshio, where the Earth's interactions and subsurface can,
Thank you very much. This is Tony Lee from JPL Caltech. I have a question to all 4 of the speakers for this session, as well as perhaps to Jerry Mill. To what extent this 2-year predictability has anything to do with the interaction of the quasi-biennial oscillation with ENSO, the later being more irregular, QBO being a bit more regular?
Antonetta, we have a couple online questions. First, Ben Kurtman says he has a question.
Oh.
Can you unmute yourself?
Thanks, Sarah. Youngji, that was a really nice talk, and I'm a little bit aware of some of your earlier work as a PhD student, and you also mentioned it towards the end, the need for capturing mesoscale ocean features in the forecast system. I'm just wondering if you might have you mentioned it very briefly, but I just was wondering if you had some more comments on that, given that some of your figures really showed, when you did comparisons with the observations, that you're really missing much of the spatial heterogeneity in the observations. And I just wondered if you had a few more thoughts about the need for increased ocean resolution there.
let's just face you.
Okay.
Hi, Ben. Thank you so much for your question. Yes, I think there are lots of contribution of the eddy activity to the surface and subsurface ocean over the Western North Pacific. And what we found was increasing ocean resolution might be helpful to capture the relationship between the sea surface height variability and the location of the ocean upfront. So what we found, there was observed the relationship between the SSH variability and the latitudinal position of the KESSH jet on the decadal timescales. But it was not resolved in the previous model, where the ocean resolution is pretty coarse, like 1 degree ocean model. But when we increased the ocean resolution like 25 kilometer, we found that relationship is much improved. So I think increasing ocean resolution might be helpful to capture the real physical relationship between the surface SSH level and the eddy activities impact onto the ocean circulation, I guess.
Okay, sorry, I think I cut the line earlier of the order of questions, so I rephrase my question to all 4 speakers and perhaps to Jerry Mill as well. The question is, to what extent this kind of 2-year predictability for some of the ENSO event has anything to do with the interaction of QBO, which is more regular, with ENSO, which is more irregular?
Well, good question. This interaction between modes of variability is really an active and interesting research question, especially in the prediction and predictability arena, like you say, because you're looking for processes and mechanisms that you can kind of try to predict to give you some skill, right? So you're looking for anything that can kind of get you there. And so there are some interesting indications that QBO and MGO could have some kind of interaction. And of course, those timescales with ENSO, there's of course a lot of literature on MGO with ENSO, that the intraseasonal MGO events, westerly wind bursts, can trigger ENSO event transitions. So I think all of those kind of fall into the category of interactions of modes of variability that have been studied kind of in separation, that now people are trying to study them in in aggregate, which I think is a really interesting research direction to take to try to give us some processes that we can try to predict and understand. And I think that's an active area of research right now.
We have some virtual questions after she answers.
Yeah. Anybody else wants to respond? Any of the speaker? Maybe Xian, I don't know where she is. You want to answer? Okay.
Yeah, we have a question. Yeah, Yoshi, we see your question in the chat.
So I have a question to Youngji, and it's a nice talk. I'm just wondering, so you show SSH signal is predictable for several years in the Kuroshio region, but just wondering, is there any predictive skill for PDO? Because that one should be related to the PDO signal, right? So I just curious, your model shows some predictive skill of PDO, how long it is, or you cannot see any predictability of PDO.
Yes, I think this is a very important question, and actually, the current research scientist at NOAA GFDL, who is Liping, has been looking at the PDO predictive skill using the coupled climate models, but we found there is no significant and powerful skill on the kind of that PDO like SST representation, because we think there are many large damping effect onto the SST, not like sea surface height related oceanic content of the ocean circulation. So the crucial variability is the part of the PDO. So certainly there might be some effect of the predictive skill of the Kuroshio extension to the PDO, but I think using SST, it is very hard to capture the kind of that decadal predictive skill in the current global climate models, I guess.
Okay, thanks.
Okay, because it's my turn. This is Elizabeth Maroon asking a question for Rob. Cool talk. And I was wondering, maybe to zip by me, and I totally missed it. Have you thought about how to use the signal to noise maximizing patterns to make some sort of like near-term prediction, like, take them and project them back into the last couple of years of observations to try to figure out what's happening? Just kind of curious if you thought about that at all.
Yeah, that's a good idea. Not yet. So I've been focusing on, as part of this project with NCAR collaborators, just trying to figure out what processes are leading to this initial condition predictability, if you want to call it that, on 50+ year timescales. But there has been a wide range of previous work, mostly not recently, mostly like in the early 2000s, late 1990s, about using these methods to more in the predictability sense on 1 to 2 year timescales. And I think that deserves revisiting now that we have all these new data sets, because I think it's a really powerful method that's in some sense been a bit forgotten. And I think that's would be a productive thing to try.
Okay, so Ben, yeah. Okay, we have a question from Ben Kertman.
I think I already asked it.
Ah, okay. Ayen. I thought you had another one. So Ayen, is your turn.
Great talk, Rob. My question is, have you tried to distinguish initial value versus forced predictability in your analysis? And I wonder whether the long predictability you showed comes from the forced predictability.
Yes, great question. Thanks. So the analysis is set up in a way that the signal noise maximization is considering the forced predictability as part of the noise. I wouldn't call that noise exactly, but for the purposes of this analysis, it is filtering out that forced predictability. So everything that's being considered predictability in this analysis is coming from the ocean initial conditions, or from, and I think there is some interesting stuff to figure out there, though we've not fully figured out what's going on yet, I think there can be interactions between the ocean initial conditions and the force response. For example, we have a hypothesis that this reemergence of predictability in around late 1990s, year 2000, could have to do with either with ocean initial state influencing how the system responds to volcanic forcing in Mount Pinatubo, or due to there's some idiosyncrasies of how the CSM2 Large Ensemble does the biomass burning aerosols, which could be relevant there and could interact with what the ocean initial state is doing. So there's only forced predictability in there if it interacts with the initial value predictability.
Thank you.